Welcome to Google Cloud AI Developer Relations Virtual Presentations. My name is Andrew Froelich, and I'm a staff member at Google Cloud AI Developer Relations. In today's presentation, we're going to discuss how to use deep learning to do social distancing in a post-pandemic period. Okay, so this is the outline. So we're going to first talk about the challenge, that is the challenges businesses will or may face in a post-pandemic economic reopening. And then we're going to look at features. What can deep learning do for businesses to sustain a post-pandemic reopening? We'll look at some use cases, how to deploy deep learning, and then finally, we're going to take a technical look under the hood. We're going to go two ways. First, we're going to look at sort of reusing pre-trained models and how to put them together to put together such a system. And then we'll also look at a do-it-yourself version for those that want to build it from the bottom up. Now, we're not going to go any code or anything. We're just going to show more of an abstract and conceptual level. So let's start with the challenge. Well, countries will want to sustain a safe environment from a COVID-19 second wave. And in this post-pandemic, there are likely to be regulations to open, and we don't necessarily know what they're going to be yet. We can presume they're going to vary from country to country. They may even vary from state to state within the country, and they could possibly vary across industries. For example, there may be one requirement for grocery stores, a different one for, say, the restaurant industry, a different one for hospitals, et cetera, et cetera. But they'll all include probably something to do with social distancing and face masks. And actually, when I say social distancing from this point on, I'm really kind of talking about encompassing all of those. Okay. And there may be actually requirements that differ depending whether it's staff, somebody employed at the business, or the public, somebody, for example, who's a customer at the business. So deep learning is adaptive, and it can learn to adapt to a varied and changing regulation. So I think this is an ideal thing for deep learning to be applied to. I don't think it would be practical with a conventional software application. So let's look at the probable features that such a deep learning system would have. Well, first, in social distancing, you need your staff to staff recognition. So you're going to have some facial recognition on just for the staff at that particular site. You'd want to be able to do staff to public social distancing. So you'll need the facial recognition again for the staff, but anonymous people tracking for the public. Okay, and then public to public. So that would just be anonymous people tracking. And then for the face mask detection, you probably want to not just tell if they're wearing one or not, but the quality. Is it an N95? Is it a surgical? Is it cloth? And you may even want to be able to tell if they're wearing it properly. For example, when I go out to grocery stores, I sometimes see people not wearing their mask properly. Sometimes I see it, here below their nose, still covering their mouth. Other times I've seen people actually just hang it off their bottom lip so they can still talk. Clearly, those are not being worn properly. And we probably would like to have a real-time alert to edge devices, either like a mobile phone or an IoT. Maybe the mobile phone is like the site manager giving them alert, or an IoT device, imagine a queue up to a cashier, and there are markings on the floor, every 6 feet where people are supposed to stand. And maybe they're numbered 1, 2, 3, 4, 5. And there's a little monitor facing the queue, and maybe the system, let's say person on number 3 is a step too far forward, and it detects it, and maybe on the screen sort of a yellow circle comes up with a 3 alerting that person that they're a little bit too close. So let's kind of look at next the use cases, how you would deploy it. So you're going to have, your cameras. I myself would recommend deploying this on edge devices. So you have an edge model. Because you're doing facial recognition of staff, you're going to have with that edge model the data for recognizing staff. Okay, and this just depicts, people and staff. So you're going to want to measure things like staff to staff distances, staff to people distances, and people to people distances. And then you're going to take all that the stuff all that you detected by the model and send it to some kind of device like a mobile phone or an IoT device or both. At the same time, you want to do the same thing for the face mask recognition or detection. So for staff, of course, you have to do the facial recognition as well as the face mask detection. And then for people, you're going to do the anonymous people detection with the face mask recognition. And again, you're going to send all that data to some mobile or IoT device in real time. And then finally, at some periodic, like once a day, you're going to sort of want to take all that data and send it up to the cloud to do something more with it. Okay. So, for example, we may, during throughout the day, we collect data locally on the face mask detection and on the social distancing spacing between public and staff to public. And then we're going to send it through some data enrichment. We're going to aggregate it down, but we're going to then sort of augment it with time information and people flow information like density over periods of time. We're going to take that enriched data and we're going to send it up to the cloud, probably through some REST interface. And on the cloud, we'll have two things. First, we'll have a visual reporting system. So just the ability to visualize that data, and that would be used by operations and planning. And then at the same time, that data is available for compliance auditing. Then additionally, we'd want to take that data and have a cloud model that does staffing optimization. This is something we already do on the cloud, okay? But in addition to figuring out, the correct staffing based on sort of the economic activity at the location, now it additionally takes into account the social distancing information to decide things like how much staff is there, when they're there, when they're at those locations, and where or how far they should be apart, whatever the optimization requirements are. So now we'll jump into the looking under the hood, the technical part. But before I do that, I want to talk about the view perspective. Now, if you think about in social distancing, if I take my camera and I'm facing straight on, I really have no sense of depth. I really can't tell the distances between people in the foreground and people in the background. So that's not going to work. Now, if I have my camera directly overhead, looking straight down, well, that's a little better. That's a Cartesian space, and I can tell the distances. But you know what? I'm looking at their heads. I won't be able to do the facial recognition for the staff. Okay, so more likely your camera is going to be above and pointed down at an angle. And when you do that, I'll call that the camera view, then you know that things that are at the same distance apart are going to be wider here at the front and narrower at the back. Okay. And so what we want to do is that if we know this volume, and we know the angle of the camera, we can warp that into a Cartesian space. So it's important to remember, and we'll talk about it in a little bit further down, the ability here to warp that camera view into a Cartesian space so we can do the social distancing calculations. So I'll start off with using sort of off-the-shelf, pre-trained stock models. You might find them from example, TensorFlow Hub or open source repos, typically called zoos. So you'd be looking for a people detection model. Okay, and you want the version of the model that doesn't do the final output, but actually doesn't have that actually returns what we call the latent space, or in the TensorFlow Hub, they call it the feature vector version, or like in a Keras zoo, they would call it a model without the top. And what these are is these are sort of like the last feature maps that are being generated by this, but before they were aggressively downsized and flattened, which is your bottleneck layer, and then go into some kind of final task like a classifier. At the same time, it will have a second output, and that will be the bounding boxes. Okay, so now we're going to use that bounding box information, and we're going to use it to cut out the people, but not out of the original image, but out of this latent space. Remember, this is a spatially preserved latent space. And we're going to use those cutouts then to train these next models. We call them our TATs. And that's a lot more efficient than starting all over with the original image and passing it through various convolutions to do the feature extraction. So the feature extraction's already occurred here. So we're just reusing that whole process downstream, which will give our model a shorter latency, that is, respond back quicker, and will be a smaller footprint for fitting on an edge device. Now, these downstream tasks will include your facial recognition, your one shot, probably take an off-the-shelf model, and then you just have a database for the local staff. That's an encoding of each individual. The social distances, well, that's actually not a model. That's kind of like a fixed algorithm. Is that warping? And then the calculation of the distances. But those can still be implemented as graph operations. There's just no learned parameters. And then a face mask detection, you take a stock object detection model and train it for your face mask detection. So let's now kind of look at do-it-yourself version. So you're going to start off with a multitask model based on object detection. Okay, it's going to have some common layers for your feature extraction. Okay, and it's going to output some high dimensionality latent space. Now, you wouldn't want to use something like a ResNet 50 here, the output, the bottleneck layer, or just before the bottleneck layer output of a ResNet 50, because those feature maps are 4 by 4. They're only 16 pixels. That's really not enough to really know the distances between people. So I'd recommend at least 8 by 8. That gives you 64 pixels. And if your camera is over a wider area, you probably want to even use a larger size. Okay, but again, from that latent space, you're going to do your people detection. You're going to output the bounding boxes, right? And then you're going to copy this latent space, pass it to the crop, use the bounding box to cut out those cropped areas of the latent space, just like we did in the previous one, and then pass them into your your final task, which you either are pre-trained or canned, or you built them from scratch. So let's kind of take an even deeper look. So we're going to look at this part right here. Okay, so your object detection, your common layers generally are going to be something like a region proposal network, or a region proposal network, or a feature pyramid network. And the output of that is actually two items. So you're going to get that high dimensional encoding, the latent space, okay? But you're also going to get the coarse bounding boxes for foreground objects. And what that means is inside of here, one of the things it's going to do is it's going to come up with candidate bounding boxes. And for each one of them, it's going to decide, is that a bounding box that contains an object, which means it's a foreground, and if not, then it's a background. And so it's going to only output the foreground objects, bounding boxes for the foreground objects. Then you're going to take that information, you're going to go through an object classifier. So for every one of those foreground objects, you're going to classify it. And one of the things you want to classify it for is a person. And then at the same time, there's a regressor here that fine-tunes the bounding box and outputs the fine-tuned bounding box. And it's usually 4 numbers, the top left coordinates and the height and the width. Okay. Now, coming out of the object classifier, this could be a multi-class classifier you might use, or it could just be a binary classifier. Yes, no, it's a person or not a person. But you're going to have your low dimensionality encoding, that's the bottleneck layer, and then finally the task. And so in the case of a multi-class object classifier, it's going to go through a softmax. And if it's just a binary classifier, yes or no, you'd use a sigmoid here. But up here, your soft labels is just that distribution, how confident it is of any particular class, or in the case of a binary classifier, how confident am I it is that object or is not that object. Okay, so let's now talk about the there we go. This crop part here and the working. Okay, so we're going to take those bounding boxes and then we're going to apply the warp into the Cartesian space. Now we can do an L1 distance measurement between every pair of bounding boxes and output that. Okay, so let's get to the face mask detection. It's kind of the same as earlier. Again, we're going to reuse that high dimensional encoding latent space and the downstream model, the face mask classifier. We're going to train it on that input, not on the original input image input. We're going to take that latent space along with the bounding boxes, use the crop function to crop out of the latent space, the area of the bounding box for each person, send it through the face mask classifier, and then we're going to output our multi-label classifier. We're going to say what type of face mask it is. Is it an N95, surgical, so forth. And then also an indication whether it's been properly worn or not. One could argue that really is a binary classification. So this might be, you might see this as a multi-class classifier plus a binary classifier. Okay, and then finally, you have your alerting system. So coming out of this part here, the L1 distances between the centers of each of the bounding boxes. Okay, and you use that to calculate the distances. Now, at this point, every one of these bounding boxes is also annotated. So first it's going to say, whether it's an anonymous person, the public, or staff. And in the case of a staff, it'll have an ID. Likewise, the classifications that go with these bounding boxes will be also annotated so they can be aligned with the bounding boxes here. And then that goes into your alert system. And just hypothetically, like red might mean there's a distance violation without face mask. Maybe yellow means there's a distance violation with face mask. And green might mean there's no distance violation. So I want to thank you for watching another one of Google Cloud AI Developer Relations AI training sessions. Thank you.